Now, if we look at the electric field and the potential distribution around a charged conductor, then we see that if this is a charged conductor, which may be solid or it may be hollow, radius is a and the charge is q, and the entire charge will be on the surface. Let's assume it's a positive charge. Then if we plot the electric field versus radius, so how does the electric field change as we go from the center towards outside and out here, then we know that the electric field is 0 inside. So from here to here the electric field is 0. The electric field is kq over r square. So for any point outside, it behaves like a point charge of charge q, and the maximum electric field would be right on the surface, and then it's 0 inside. The electric potential is outside, it's kq over r, so it behaves again like a point charge if you're outside. But once you're inside, then the electric field is 0, and the potential is the gradient of the potential is the electric field. So this is 0, the gradient is 0, which means it's a constant. So whatever it is on the surface, which is kq over r, and r here is equal to a, then the electric potential inside is constant. Now, to compare it with a uniformly charged sphere, which is essentially an insulator, so that the charge q, we have some same charge q or maybe different, it's distributed throughout the volume of this sphere. So it's not a hollow sphere. This may or may not be hollow, but this has to be solid, and the charge has to be distributed everywhere inside it uniformly. And it's also radius a. So the electric field inside, which we saw in the previous chapter, was kqr over a cubed. So it keeps on increasing linearly from the center to the surface, and at the surface it will have a value of kq over a square, because r becomes equal to a. And then outside it decreases in the same way as it does here. So it doesn't matter whether it's a conductor or insulator, so far as you're outside, you want to find the electric field outside it. Now the electric potential for this case outside the sphere, so for r greater than a, this is r equals a. For here it's the same as it is here, so it's as if it were a point charge. So if you're over here, this behaves like a point charge, and on the surface it will be kq over a when r is a. But inside it, the potential keeps on increasing according to this equation, and at the center of the sphere it reaches a value of 3 by 2 kq over a. This is kq over a, so whatever it is on the surface, it's 3 by 2 times that in the center, irrespective of the diameter. So whatever it is on the surface, it's 1.5 times that right in the center. So this gives us the electric field for a conductor and an insulator. We now do an example of a case where we have a solid sphere, and this is an insulating material. It has a charge q1, which is uniformly distributed inside the surface, inside the whole volume. And we have a metallic shell or a conducting shell that is spherical and concentric with the inner one. So they both have the same center of at the same center is the same for both of them. And the charge on the outer one is minus q2. So this has a plus q1 charge, this is a minus q2 charge. So whatever is q1, this is double of that, and it's negative. And we want to find the electric field inside this region, in this region, inside the metal, and outside. So for inside, if you want to find it here, we make a Gaussian surface here, and then the electric field here would depend only on the charge that's inside, and we did that in a previous case, and the electric field becomes kqr over a, where r would be the radius up to that point, wherever we want to find the electric field. This charge has no effect on the electric field here because that's a Gaussian surface and this charge is outside the Gaussian surface. And any charge outside the Gaussian surface will have no effect on the flux, and the flux, because that's equal to Q in over epsilon naught. So because there's no charge inside, there's no flux due to this charge, and so whatever electric field we have will be dependent on only this charge. Now, in region 2, if you're here, we make a Gaussian surface, then the charge inside this surface is Q1, and as R is from here to here, and it will be from any point at between A and B. So for R between A and B, it's simply KQ over R square, where Q1 is the total charge here. This is going to be Q1. This is Q1. And again, this has no effect. Now we come to region 3, which is in here, and because it's inside a metallic material, the electric field here is going to be 0. Now it's not 0 here because there's a charge in here. The effect of this charge is 0. So in here, the electric field is going to be 0. And now when we are outside here, this is R, then we can make a Gaussian surface here, and we'll just use the same thing. So Q in is minus 2Q plus 1Q. So it's going to be just add the two charges. So 1Q and minus 2Q. That's the Q total charge inside, and KQ over R square. Again, this whole thing behaves like a point source if you're outside. The total charge Q1 minus Q2. So that would be the electric field for R bigger than C.